Hello everyone, I'm Norman Wildberger. Thanks for joining me on this adventure in algebraic calculus and de Castelao-Bézier curves. Today a very important lecture where we're going to introduce a new point of view towards vector arithmetic and the notation that we use to express physical notions like velocity, acceleration, etc. And we want to really point out the very big difference between the notion of a point, which is sort of stationary or fixed object, and a vector, which we want to think about as being a relative object, something which expresses the relationship between points. So I think this is a really useful arithmetic that we're going to employ here, which will be of interest also to physicists and engineers. Okay, so our motivation is that we've been looking at cubic de Castelao-Bézier curves and say with control points P0, P1, P2, and P3. And we've seen that we can express that as a combination of the points with these coordinates, which are functions of t. They are Bernstein polynomials in t, in this case, the cubic ones. Now, this interpretation actually has an interpretation as an affine, or sometimes called a convex combination, because of the crucial property that the sum of the coefficients is identically 1. Okay, so please, let's make note of that. This is an important property of the Bernstein polynomials. If we just take 1 minus t cubed plus 3, 1 minus t squared t, plus 3t squared, 1 minus t plus t cubed, we see that's really just the expansion of what we might say is 1 minus t plus t. So you think of 1 minus t as one term and plus t as a second term. This is really just a binomial expansion, power 3 of that. And since 1 minus t plus t is actually 1, necessarily the sum is going to be 1 cubed, which is 1. All right, so that's really important. That's telling us that this combination is a combination, almost a geometrical combination, which we're going to talk about, of these points P0 and P3. And actually, if t is between 0 and 1, implies that this point is always in the convex hull of the 4 control points. Now, we've seen that we can rewrite this by expanding it out and expressing it as a polynumber in t, okay? So constant term, linear, quadratic, cubic terms. We get these sort of coefficients now, which are actually points, okay? So there's a P1 minus P0 here, there's a P0 minus 2P1 plus P2, and there's this curious 3P1 minus 3P2 minus P0 plus P3 over here. Now, what we're going to want to do is to interpret these things as vectors, okay? So this second equation here, we're going to see has the form of a point, that's a point, and this is actually a vector, and this is a vector, and this is a vector. So in that interpretation, we are creating an arithmetic where points and vectors combine naturally, okay? So this is what I want to explain today. So this sort of subtractive arithmetic of vectors that I'm going to explain to you is following a recent paper of Joshua Ho and myself. The paper is called A Case Study in Universal Geometry, Extending Apollonian Circles to Relativistic Geometry and Finite Fields, 2020, and a link to that will be below. You can have a look at it. And the entire story is, very interestingly, closely related to Archimedes' law of the lever. So all kinds of interesting things that we're going to introduce today, a lot of them will be familiar to you, but I want you to look at things in a slightly new way, okay, especially with new sort of arithmetical notation. Okay, let's have a look at this diagram here, okay? There's 3 points in the plane, A, B, C. These are points. And there's a 4th point in red, P. And up here we read that P is 1/2 A plus 1/3 B plus 1/6 C. Now, this is a very special kind of linear combination. It's a combination where the sum of the coefficients is 1. Okay, that's going to play a really important role for us. And physicists know that this means that P can be thought of as being inside this triangle formed by A, B, C, with these numbers sort of representing weightings. Okay, so what's really happening here is that we can think about having a weight of 3 at the point A, a weight of 2 at the point B, a weight of 1 at the point C. And then this point P will be the point of balance of this configuration of 3 points. So imagine that the triangle itself is a solid with negligible mass, and all the mass is at the three vertices. So the point P then is exactly the point of balance. And what's involved here is Archimedes' law of the lever, which says that if you have a lever with masses m1 and m2, and the point of balance will be such that the total moment is 0. What's the moment? Well, the moment is what you get when you look where the fulcrum is, and you look at the vectors emanating from the fulcrum or the center to the masses. So maybe vector v1 to m1, vector v2 to m2, okay, from the center. And then Archimedes' relation can be expressed as that this will be a point of balance precisely when m1 times v1 plus m2 times v2 is the 0 vector. So it's actually a vector equation. Okay. This is too often stated somewhat incorrectly in terms of distances, and it's made into a metrical thing. So it's not a metrical thing. It's an affine thing. It's a concept involving only vectors. Now you might be tempted to rewrite it as d1, like this length times the mass is equal to this length times the mass, but please don't think about it that way. You want to think about this as being a vector relation, and that's much more suitable for generalizations. So for example here, if we look at the corresponding thing, we can think of this point P as the center of mass of this configuration. And what that means from an Archimedes point of view is that if you take this vector here from P to A, okay, at that vector there, and you multiply it by 3, okay, it's a bigger vector, and then you add the vector PB and you multiply that by 2, and then you take this vector from P to C and you multiply it by 1, that the sum of those will be 0. Okay, so maybe we can see it like this. So suppose we start here at P, and I'm going to go 3 times, 1, 2, 3 times in the direction to A. And now I'm going to go twice the direction from P to B. So P to B would be from here, that'd be P to B, and then once more would be from P to B down to here, okay? Or maybe down here. And then we'd have to go 1 over from the PC direction. That would bring us back to P. So the net effect of the sum of these 3 weighted vectors is a total of 0. And that is the two-dimensional version of Archimedes' law of the lever. All right. So what we're going to do today is to explain a beautiful, somewhat novel way of capturing what a vector is in order to be able to make calculations in such a situation very easy. We're going to be able to understand the various ratios that appear in this barycentric coordinate kind of diagram very easily as direct consequence of simple manipulations of essentially this formula. All right, so let's have a look at the same relationship now here in GeoGebra actually. So here's the points A, B, C. Here's that point P, which is this particular combination of A, B, and C. And you can see what happens as we move things around. Okay, this point P will always have this particular relationship. And what characterizes this relationship? Well, you can describe it in a number of ways. One way is to describe it, say, in terms of these additional points, D, E, and F, formed by these Chavian lines. Okay, that's called a Chavian configuration. Because the various ratios of the sides formed here form an important have an important relation that was discovered by Chava in the, I think, 1700s. Maybe it was even 1600s. And it's all contained in this equation. So let's have a look, for example, at this side here, okay, B, D, and C. According to the weighting I was telling you before, this is a kind of a balanced situation where we have a weight of 1 here and a weight of 2 here. So if we just restrict our attention to this line here, imagine having a mass of 1 at C and a mass of 2 at B, then this is going to be the point of balance. And the crucial property then is that the ratio of this vector to this vector is 1 to minus 2. or maybe another way to put it, the ratio of this vector from B to D to C, that's in the ratio of 1 to 2. Okay. That's just a statement of Archimedes' law of the lever. So we have a ratio of 1 to 2 here. And on this side here, we have a ratio of 1 to 3, okay, where we're going in this direction. So this vector and this vector are in the ratio of 1 to 3. So for example, I can actually make some vectors and show you that. So vector from A to E, okay. There it is. There's that vector A to E. And the vector from E to C, there it is there, okay. And yes, indeed, this vector V is 3 times the vector U. They're in the same direction, and this one is exactly 3 times this one. And that will be maintained, oops, sorry, don't want that one. That will be maintained even if we move the diagram around, okay? So if we change our coordinates, if we change our frame of reference, then yes, we're going to have different expressions for these vectors, but these relations are going to be maintained. This vector V will always be 3 times the vector U. And over on this side, the ratio is given in terms of these numbers. So weight, a mass of 3 here, a mass of 2 here. So this is in the ratio of 2 to 3. So one of the things we're interested in here is to clarify the distinction between points and vectors. Okay, so A is a point, E is a point, but this U object, which is this displacement from A to E, is not a point. It's a vector. It's a different kind of object, even though it's very closely related to points. Now, in a lot of undergraduate courses, especially in maths departments, the distinction between points and vectors is confused or finessed. And as a result, students often have a lot of problems, especially when math students are learning about physics, and you have some particle making a trajectory in the plane, and at every point there's a velocity vector. So we draw the velocity vector at the point that we're talking about, but then the coordinates really suggest that the velocity vector is down here somewhere where the origin is. Okay, so there's a bit of confusion as to what exactly the difference is between points and lines. And that happens in linear algebra too, where people like to work in a vector space. Typically you're working in a vector space. When you think about lines in the vector space and vectors or points in the vector space are like vectors. So the distinction between points and lines is easy to get confused about. But what we want to do in this affine geometry is very clearly to distinguish between points and vectors. Okay, that's going to be really important for you to keep this in mind. So points are fixed things, don't move around, they're there, they are. And vectors represent relationships between points. And vectors have this translation property, right? For example, if I make some other point here, here is a new point, okay, G. There's the vector U. So GeoGebra will, for example, allow me to make a vector from a point. So I can vector from a point. Do I do this one first and then G? Okay, that'll work, yeah. So this vector W, okay, is a copy of U, but now it's sort of positioned at G. From a vector point of view, this vector U and this vector W are exactly the same. And the reason is because, and maybe it's clear if I move this over a little bit, the reason is because geometrically, the relationship between these 4 points is given by parallel lines. AE is parallel to G prime, and AG is parallel to EG prime. So purely with the notion of parallelism, we can define equality of vectors. In other words, we can translate vectors. Okay? But vectors themselves are not fixed in the plane, therefore, but points are. So we want an arithmetic that really properly captures all this stuff, and that then subsequently allows us to understand this barycentric coordinate kind of situation very easily, and allows us to immediately deduce what all these various ratios are. For example, what's the ratio between this vector from F to P to the vector from P to C? Can you calculate that very quickly? Well, at the end of this lecture, you will be able to. Okay, so let's go to the arithmetic now, starting with affine points, which are given by pairs of numbers in square brackets. Say P is equal to AB and Q equals CD. So those are 2 affine points in some frame of reference. Then, The vector between them, v, which we denote with round brackets and is given by the difference in the coordinates, so c minus a, comma, d minus b, we are going to introduce this notation for it. We're going to just refer to that vector as the difference q minus p. Okay, so it is not the case, note very carefully, it is not the case that we're assuming a prior arithmetic of affine points. Okay, in particular, the sum of p plus q is not defined for us. Okay? We're just defining this new expression, q minus p, for these affine points and calling that a vector. Now, traditionally in engineering and math and physics, vectors are often represented with like qp with an arrow over it, or pq in this case with an arrow over, or sometimes it's an arrow underneath, or sometimes it's a little wavy line underneath or over. So there's quite a lot of notation. And in fact, often the notation for a vector has a little harpoon, so it's kind of a one-sided barb, not a two-sided barb. Okay. What I want to suggest is that we should try to let go of all those notations and move rather, okay, to a purely arithmetical form for vectors. If we want to talk about the vector from p to q, we will use the expression q minus p to denote that vector. This particular quantity here, pq with a standard arrow over it, let's reserve that for the directed edge from p to q, by which we mean the pair of points p and q. So it's really a two list of points. So this directed edge cannot be translated. It's at p and at q. Okay, so we're not going to use this for vectors. We're going to rely more on this difference notation. Then we will also allow ourselves, once we've defined this vector v, to write that the point q is the point p plus the vector v. Okay, so we're going to allow ourselves to combine points and vectors, but always with the point first and the vector second. Okay, and typically for us, points are capital letters and vectors are small letters, and in terms of coordinates, points are square brackets and vectors are round brackets. So it shouldn't be too hard to distinguish them. So we are not going to allow, for example, the expression v plus p. Okay, that's not going to be defined for us. P plus v makes sense. And in terms of coordinates then, the point AB plus the vector RS gives us the point A plus R, comma, B plus S. I might note here that the associative property is then defined. And what is that? That if we have a point P and we add to it a vector V, so that's a new point, okay? So now it's a new point, so we can add another vector W to it. So for a point P and vectors V and W, we have, so this P plus V plus W, that should be another point, right? That's going to be the same as the point P plus the vector V plus W. So vectors can be added. Vectors can be scalar multiplied. It's an interesting thing that we're defining vectors essentially in a subtractive way. But once we've done that, then we can add vectors. So addition of vectors is the extension of the following. Okay, let's say you have P and Q. Okay, so Q minus P, that's a vector. Here's another vector, the vector R minus Q. Okay, we can tell these are vectors because they're differences of points. And how are we going to add these two vectors? If we add them, we are going to get R minus P, which is another vector. So this is the arithmetical analog of the fact that, that you put the tail of one vector at the head of the other, and then the result of the addition is from the tail of the first to the head of the second. Okay, great. Now we're in a position to describe lines really effectively, because we have this notation of taking a point and allowing ourselves to add a vector. So, up till now I've been sort of informally talking about, affine expressions of the form 1 minus TP plus TQ. Remember, this is the basic construction that we use to describe how the de Castelao-Bezier curve results from the control points. We took the de Castelao-Bezier control points and made lots of combinations like this. But now we're in a position to say more precisely what this really is. Okay? Because arithmetically, we can rewrite this as P plus T times Q minus P. Okay? And now we see what that means. That means we're starting with the point P, and we're adding a multiple T of the vector from P to Q, the vector Q minus P. And if the multiple T is arbitrary, well, that means we're allowed to go in any direction. So that describes the entire line, PQ. While on the other hand, if we're interested in just the segment from P to Q, well, that's described by points T in the segment 0, 1. Okay, so this gives us a natural orientation to something like this. So let's also introduce notation. So the combination let's write affine. So it's not really a linear combination in that these coefficients are not arbitrary. We're not taking T1P plus T2Q. No, we're taking 1 minus TP plus TQ. That is an allowable affine combination. This is another affine point. We take affine combinations, we get another affine point. And the crucial thing about the affine combination is that the sum of the coefficients is 1. The sum of the coefficients is 1 for an affine combination. How about a vector sum? However, we are allowed to take arbitrary linear combinations of vectors. And we get more vectors. So for example, if we look at the combination, say, Q minus P, so that's the vector from P to Q, and we add 3 times the vector, let's say P minus R. That is the vector from R to P. Are we allowed to add these things? Yes, we're allowed to add vectors. And what do we actually get when we do that? Well, we just do the arithmetic. We get Q. How many P's are there? 3P minus P, that's, I guess, 2P. So plus 2P and minus 3R. This is a vector, okay, which is the sum of the vectors, the first vector that we got, plus 3 times the second vector. And it's interpretable in a number of ways. For example, this thing is a vector. And we can check that, which is checked because the sum of the coefficients is 0. The sum of the coefficients is 1 plus 2 plus minus 3. That's 0. Okay? Because, why is that? Well, because the sum of the coefficients of this thing is 0. It's Q minus P. There's a plus 1, there's a minus 1. The sum is 0. Over here, the sum of the coefficients is 0. Plus 1, minus 1. If we multiply this by 3 and add them, it's not going to change the fact that the sum of the coefficients is 0, because we're just taking lots of zeros and combining them, maybe taking 0 plus 3 times 0. It's still 0. Okay? So this is the critical difference between points and vectors. Okay, so it's so important. I'm going to say it again. It's really just an observation. It shouldn't really be called a theorem, but let's make it a little bit official, okay? affine points are combinations of points where the sum of coefficients is 1, while vectors are sums of, or combinations of points, let's say, of points where the sum of coefficients is 0. So we can immediately tell whether an expression in a linear combination of points is actually a point or a vector, or it's not defined. If the sum is not 0 or 1, then this thing doesn't make sense to us. So let us go up here, back to the original motivating example. So I've already mentioned now that this first thing here is actually a point. Okay, you can see that's a point because it's a sum of points, and the sum of the coefficients is, as we pointed out, already equal to 1. Now when we write it like this, we can now more clearly see what the significance of these terms here that are appearing is. So this p1 minus p0, that's obviously a vector. That is, in fact, the vector from p0 to p1. And what about this thing here now, the coefficient of t squared, apart from the 3? It's p0 minus 2p1 plus p2. That is also a vector because the sum of the coefficients is 0. And which vector is it? Well, that's actually the difference between the vector from p0 to p1 and the vector from p1 to p2. So the vector from p0 to p1 is p1 minus p0. Okay. The vector from p1 to p2 is p2 minus p1. So if we take that second vector, p2 minus p1, and we subtract the first vector, which was p1 minus p0, okay, we're going to get p2 minus 2p1 plus p0. So this is a difference of vectors formed by subsequent points of the de Castelao-Bezier polygon, but it's also a vector. And what about this thing? 3p1 minus 3p2 minus p0 plus p3, right? We've seen this is quite an important thing. Well, it is also a vector because the sum of the coefficients is 3 minus 3 minus 1 plus 1. That's 0. That's a vector. Okay, and in fact, it has an important geometrical interpretation. In fact, all of these vectors are going to be important for us. But we want to be able to look at an expression like this and say, aha, these are points. These are vectors. So here we have a point, and then we're adding a vector, and then we're adding another vector, and we're adding another vector. And the sum is, or the result is, a point, because a point plus a vector is a point. Okay, so now I'm going to show you how this understanding really helps us understand barycentric coordinates and ratios like involved in Cheva's theorem and Menelaus's theorem. So let's have a look at this diagram, okay? So we said that P is the point 1/2 A plus 1/3 B plus 1/6 C. And there it is geometrically. Now we want to analyze various other things that are involved here. For example, we'd like to get expressions for D, E, and F, for example. So I'm going to rewrite P, okay? So P, which is this, okay? I'm going to rewrite it as A plus something. A plus something. Well, what am I going to have to do? I'm going to take this thing here, cheat for a second. Okay, I'm going to stick it in here. What do I have to put in here in order for this to be true? Well, I just have to put a minus sign in front of this one here. Okay, you will agree now that this is just a rewrite of this. But now notice that I've rewritten it as a point A, plus, hey, this is a vector. Why is it a vector? Because minus 1/2 plus 1/3 plus 1/6 is now 0. That is a vector. And, well, what kind of vector is it? It's a vector from something to something. Well, I can rewrite it as something minus something. Okay, so I'm going to rewrite it as something like this. So I'm going to rewrite this, what's inside here, as the vector. Maybe I'll put a multiple, say lambda. I'm going to rewrite it as lambda, some multiple lambda of the vector from A to D. What's the vector from A to D? It's D minus A. Okay, so now I want to figure out what is D and what is lambda from this equation. Okay, so how do I make these things match up? Well, I have to make altogether the A's. There's going to be a total of a half of A. So I've got an A here, so I better have put a plus half here in front of this D minus A. Okay, then the total A will be 1/2 A, which is the same as this. Well, just comparing that with this, then we see what this really is it's A plus fraction 1/2. What is this D? The D is just, I have to take this thing here, okay, and I'm going to have to multiply it by 2. 2/3, 2/6C minus A. So I'm just taking this thing here and rewriting it. I've pulled a half out. Okay, I've pulled a half out. So I get a minus A, pulled a half out. So I've got 2/3 B here plus 2/6C equals. And what does that tell me? That is A plus this fraction can be made as 1/3 C. And this then is the point D. So I've just rewritten it in this form, and so we can deduce, so we find that the point D is actually equal to 2/3 B plus 1/3 C. Is that a legitimate combination? Well, the sum of the coefficients is 1, so that is a legitimate combination. And this is then an accurate representation of this point D. It's really in the, it's given by this weighting here. That's 2/3 of B and 1/3 of C. This is where Archimedes' lever would balance on this side here if you had a mass of 2 and a mass of 1 here. And another way of saying that is that the ratio of this vector to this vector is in the ratio of 1 to 2. Another immediate consequence of this is that the vector from A to P is 1/2 of the vector from A to D. So also the vector from A to P, how do we express that? Well, that's P minus A. And that's going to be 1/2 of the vector from A to D, which is D minus A. So you see that this expression here and just simple manipulations, just using grade 3 or maybe grade 5 algebra, allows us to express P in such a way that we can immediately identify what this point D is and immediately identify what the ratio of these vectors are here. Okay, now I'll leave it to you as an exercise to do the same thing for these other points. So now we have a very flexible and powerful but simple approach to vectors, which is going to be really useful for us as we investigate these de Castelnau-Bezier curves and the relationships with their control points.